Hi, physics class. This is a video to replace the video that failed on my Wednesday, December 2nd's review for our Unit 2 test tomorrow on Friday. So here we go. We do a quick review of what we did in the chapter, and then we'll go through the review sheet. First thing I want to talk about is distance, displacement. What was the difference between these? Distance just has a magnitude, right? So like 5 miles. And we call this a scalar, right? So you can think of distance as being like an odometer or a pedometer, just how far did you go? Displacement, it does have a magnitude, let's say 5 miles. But it also has a direction. Let's say north, right? Because it has a magnitude and a direction, we call this a vector. Okay? We call this a vector. So if somebody starts off at the school, walks 5 miles this way, walks 5 miles back, how far have they walked? 5 miles out, 5 miles back, they've walked 10 miles. So our distance equals 10 miles. Remember our displacement, where did you start, where did you end? In this case, it's the same place. Our displacement is 0. So I want to be careful as we do those. All right. Let's do a little bit more of an example of these because I want to add some vectors, and that's kind of what I did there. So I did a one-dimensional addition there. So we could do it this way. So if you start at the school, you walked 5 miles. What if you walked another 5 miles? Kept going. What would your total distance be here? Would your distance be 10 miles? What's your displacement? It's also 10 miles. So why is that different? Both of them have the same distance, but their displacement's different. The displacement's different because what did we do? In our first example, they walked back. What is that? That's a negative 5 miles. We have to put the direction in there. We're putting a vector on it. Negative 5 miles. We added together 5 plus negative 5 gives you 0. Here on this example I gave here, 5 plus positive 5 gives us 10. So when you're doing vectors, it's very important to know what direction they are. In one dimension, it's real easy. You're either positive or you're negative. You're either left or you're right. You're left or you're right, or you're up or you're down, right? So it's very easy, positive, negative. 2 dimensions will get a little bit harder. Let's go to 2 dimensions. Say we have a vector. And let's say that this vector starts off, let's make it easy. The length of this vector, it goes 3, goes to the right 3, goes up 2. Let's say it does that. Let's add to it another vector. And let's say for this vector that it's going to the left, so it's a negative number, but it goes up 3. How are we going to add those 2 vectors together? We can do it graphically. And if we do it graphically, what are we going to do? I'm going to say, well, we're going to start with your green vector. I'm trying to make these the same size. Start with, and then add your blue vector to it. What's our resultant? So when we add them together, we drew our first vector. Our second vector, we placed its tail at the head of the first. Call that head to tail. And then we find our resulting vector or our added vector. We're going to start at the beginning where our first vector was. And we're going to go to the end of our second vector. So I'm going to call this the result. Let's call this A. And let's call this B. Okay. What I want you to see here is it also won't matter whether we start with B and add A to it. So let's do it this way. If I start with B, I'm trying to make these again about the same size, and now let's add A to it. Let's draw our vector, our resultant vector. We're going to start at the beginning of the first one, go to the end of the second one, and hopefully you can see these two R's. These are roughly the same. Again, I'm drawing them so fast I'm not doing it to scale. But what I want you to see is that when we take vector A, we add it to vector B, we can get our resultant vector. We can also add it the other way around. It does not matter which one you start with. The order does not matter. Okay. Now we could also do this, in addition to doing it graphically, we can do it mathematically. We can do it mathematically. So let's kind of put these guys on a grid. Okay. We said our first vector was a 3, 2. So let's draw a vector that goes over 3, 2. Went over 3, went up 2. So there's our vector A. Let's put our vector B on top of that. What was our vector B? It went back left 2 and went up 3. So here's a 1. Here's a 5. All right. So there's our vector B. Now I just put those on a graph and I put some numbers on it so we can see them a little bit easier. All right. If we want to do our resultant vector, we can do it mathematically. Let's take vector A. And we said that it went up to the right 3, and it went up 2. So that's how we would do it, right 3, up 2. What would vector B look like? It went to the left 2, so we have a negative sign, left is negative, and it went up 3. What does our resultant vector do? We're going to just do math like we normally do. Whoop. We're going to add that 3, rather x's together, 3 plus negative 2 gives you a 1. We're going to add our y's together, 2 plus 3, that gives you 5. Right, so we're going to see our r vector is 1, 5. And that's exactly the same thing we see up here in our chart. So you can add them via math like this, or you can add them pictorially like this. You're going to get the same answer. You're going to get the same answer. I want you guys to see that so it's easy enough to see how you're going to add vectors. Next thing I want to talk about very quickly, we're going to do components. What do we talk about for components? If we have a vector, we're going to break it into components. We're going to put that vector going down here to the x to the y-axis. We're going to call that the a component of the y component of our vector. We're also going to draw, let's see, we do something like that, vy. This is going to be the x component of our vector. Right. So if I kind of do this differently, that's like vx, and this would be vy. All we did was just take that vector and we broke it into its horizontal and vertical parts. So real easy. Draw a line straight down, that's your y. Draw a line straight out to that point, that's your x. Right? It's important to do it so we have our y's and our x's there. Right? So we can take this simple vector and we can break it down into a y component and an x component. That's what I mean by breaking it into components. What's nice about this? This is nice about this because this is a right angle. X and y are right angles. So if we want to find the magnitude of v, we put those bars around it like that. Like almost like an absolute value sign in math class. We're going to call this the magnitude of v. What is it equal to? We use our Pythagorean theorem, right? Because v is our hypotenuse. So we're going to take the square of one leg, the square of the other leg, and we'll take the square root, and that gives us the length of our hypotenuse. Right? So we use Pythagorean theorem. How about our angle? We're always going to measure our angle with respect to the x-axis, like I've drawn it there. How do we measure our angle? simply the inverse tangent of vector of the y component divided by the x component. Right? Easy peasy. I do want to take a minute and talk about angles, how we measure angles. If we have a vector here, we're like, well, it's not. We just did that one. That was an easy one. Let's say our vector is over here like this. What's our angle for this vector? Remember, I want you to do it with respect to the positive x-axis. So that's the angle I'm looking for. That's the angle I'm looking for. I'm not looking for this angle. Don't give me that angle. That's the angle with respect to the negative x-axis. So what's the difference here? If you're doing your math, oftentimes my hunch is when you're doing your math here, you're going to be saying, okay, there's our height, there's our length, right? Here's our x, here's our y, and you're going to do all your math and you're going to come out. The angle you're going to calculate here, right? How does that relate to how does this red theta over here on the left relate to the blue theta on the right? 180 minus the red theta is going to give us our blue theta. All right, so you need to be careful when you're doing your directions. It's very, very important. We're talking about with respect to the positive x-axis when we measure our angle. I want to get on that standard so we're all talking the same. The other thing I want to do is let's take a difference. What if our vector was in the negative direction? Right? What if our vector is in the negative direction? Well, we could measure our angle with respect to the x-axis in two ways. Right? We could measure it this way, so we could go counterclockwise. This is the positive direction when we do that, remember for your math class. But we can also measure it in the negative direction. Right? The negative direction, that's clockwise. So if we just take this angle here, let's say we measured it, and we came out and we found that this is 225 degrees. Hopefully that makes sense. By looking at these two pieces add together to 360, we know that this one's going to be negative 135. And it's negative, right, because it's in a negative direction. Negative direction. Now, which one do I want you to use? I want you to use the smallest of the numbers here. Which one's smaller? The 135. So I'd rather you gave me the smaller number here. Give me negative 135. Right? Again, these are just conventions. These are standards so we can say that we're all on the same page. Right? So if you see a negative angle, we know we're talking about below the x-axis. We see a positive angle, we know we're talking about above the x-axis. Makes things a little bit easier just to visualize for our brains. All right. Next topic we talked about was relative velocity. Relative velocity. So let's say we have a car. And somebody in that car drops a red ball. Now the person in the car, what are they going to see when they drop that red ball? That red ball is going to look like it falls straight down. Awesome. Somebody standing outside the car, standing with the earth, what are they going to see? They're also going to see the red ball fall straight down. Because the person in the car and the person on the standing on the ground, they're not moving with respect to each other. So they have the same frame of reference. So they're going to see the same thing. What happens though if that car is moving? Person in the car drops the red ball. If you think about it, if the car is moving, the ball and the car are moving the same velocity here. They're moving the same velocity here. So for every unit, for every second that the ball is falling down, it's moving the same direction as the car. Where's the person in the car going to see the ball land? To the person in the car, they dropped it here. The person in the car is just going to look like it fell straight down to them. Right? Because it just looks like it's going to fall straight down. Now, if you try this on your own, you're going to see it's going to look a little bit backwards because of air resistance. What's the person on the ground going to see? They're going to see the ball started here, and they're going to see it go all the way over like that. We're going to see it land at the same point, if you will. But our velocities are relative to each other. They're going to be off. They're going to be different. This is what I mean by relative velocity problem. Right? These things are moving. One frame of reference is moving with respect to the other. We need to be careful when we're talking about these. We need to be very careful when we're talking about these. So if I asked for the velocity of the ball when it hits the ground, the velocity of the ball when it hits the ground, our person over here in the car, right, they're going to think the velocity went straight down, and they're going to be able to calculate that velocity straight down. What's the velocity the person on the outside is going to see? Well, they're going to see it fall from that same height over here to that same distance here. So the person on the ground is going to see the same thing. The ball's going to have that component of its vector. The thing is, though, because the car was moving, there's another component to this velocity, right? So this is the velocity of the ball with respect to the car. This is the velocity of the car with respect to Earth. What does a person standing on the Earth see? Person not in the car. We're going to add these vectors together, just like we've been doing in the past, simple vector addition. We're going to start at the beginning and draw our arrow to the end. So the person on the ground, what are they going to see the ball look like with respect to the Earth? That's that vector right there. So this is what we call a relative velocity problem. The vector of the ball with respect to Earth is equal to the vector of the ball with respect to the car plus the velocity of the car with respect to the Earth. Now, I chose my subscripts purposefully because I want you to see here, we've got to see at the end of this one and see at the beginning of this one, they kind of cancel out, right? And then we have the B and the E. So it's just a simple vector addition problem. Let's give an example of that where I want you to work through it. Let's say we have a stream, and that stream is flowing south at 3 meters per second. Let's say we had a little boat, and a person's in the boat, and they're trying to go across a little raft. They're trying to go across our stream. Well, if they're measuring their velocity with respect to the stream. So what are they going to see? They're going to see that they're crossing at 1 meter per second. Okay. So this is the velocity of the boat with respect to the river. This up here in the blue, this is the velocity of the river with respect to the Earth. Okay. We got to add those two vectors together. So somebody's sitting on the ground. What are they going to see over here? They're going to see, they want to see what's the velocity of the boat with respect to the Earth. Boat with respect to the Earth. If we look at what we just did up above here, we can say the velocity of the boat with respect to the Earth is simply the vector sum of these guys, right? It's the velocity of the boat with respect to the river plus the velocity of the river with respect to the Earth. Okay. Just a simple velocity, just simple vector addition problem like we've been doing. So relative velocity problems, they're just simply vector addition problems. Be careful how you define your vector so you know which one you're talking about. The last thing I want to talk about is projectile motion. What do you mean by projectile motion? Only gravity. No other forces. No other forces. All right. And we went through a whole bit. I'm not going to derive it here right now, but what I'm going to do is I'm going to show you we started with our two basic kinematics equations. XF equals x0 plus v x0 t plus 1/2 a, and I'm going to put a little x here, acceleration in the x direction, times t squared. Well, I'm just leave it as a, sorry. And we have velocity equation, vxf equals vx0 plus at. So those were our two starting kinematics equations. Now what I want you to see here, when we apply this to a projectile motion, in a projectile motion, we know a couple things. We know acceleration in the x direction is 0. The only force acting on it is gravity. So acceleration in the x direction is 0. We also know that because the way I'm going to be doing them, I'm always going to give you a situation where the velocity, the initial velocity in the y direction is 0. We're going to keep ours simple. If you were in AP physics, you would do some where the y initial is not 0. So how does this simplify our equations? Just give them to you. xf equals x0 plus vx0 times t, right? Because our a falls out. There's no acceleration in the x direction. How about our y? Because we can apply whether x or y to this. They're independent of each other. y0. Our vy0 is 0, so we don't have that middle term, but we do have the final term, 1/2 at squared. But further, we know, right, gravity is negative 10 meters per second squared. So this we can rewrite. Let's put gravity in. Our x equation, our y equation. Not too difficult. We can really use these. How about for our velocities? vx0, sorry, vxf equals vx0. Well, there's no acceleration in the x direction, so we don't have another term here. What's that tell us? Our velocity is constant. No acceleration, we have a constant velocity. vxf is the same as vx0. How about vy0, vyf? We start off, our vy is 0. Vy of 0 is 0. All we have to do is add at. Remember, our gravity here is negative 10. So again, 4 simple equations, and all we're going to be doing in solving projectile motion is using those 4 equations. Let's go on and we'll do some projectile motion problems as we do our review. But I wanted to just go through there and remind you of that. But so typically, let me do one quick look here. Typically, we're going to give you some sort of an example or something starting at some sort of height. And I'm either going to give you the height, delta y, or I'm going to give you the velocity in the x direction. Right? Something, the motion of this guy is going to be something like this. Right? It's going to have some initial velocity that's only horizontal. It's going to fall down and hit the ground. That's what we mean by a projectile motion. So let's do our example problems here. Take what we just reviewed, put it to work. A dart is fired horizontally. Another dart is dropped. They're dropped in the same height. We're going to neglect air resistance. We often will do that in physics class. Which dart hits the ground first? Well, what I want you to see is what determines when the dart hits the ground. That means when YF is 0. So we need to use our YF equation. So there's our Y equation. Is there anything in there that talks about the horizontal velocity from the dart gun? No. No, there's no Vx0 here. So what does this tell us? They hit the ground at the same time. Because they had the same initial height, and they're both going to the ground. They had the same final position. They hit the ground at the same time. Let's look at our second one. If a rock is dropped from the top of a sailboat's mast while the sailboat is moving at a constant velocity, it will hit the deck. Will it hit the deck at the same point of the boat where it rests? So let's draw a little example of a boat. I want you to think about this. So if we drop our rock from the bottom of our mast, let's think of the boat standing still. That's easiest. What are we going to see? That rock's going to go straight down. It's going to drop straight down. Now, if we want to do the same thing, if our boat's moving, if our boat is moving, right? If it's moving and there's no air resistance, then for every little meter that the boat goes to the right, so is the ball, because they started off with the same horizontal velocity, and that horizontal velocity is not going to change. If that horizontal velocity doesn't change, where's the ball going to land? The same place. So the person on the sailboat isn't going to see a difference whether the boat's moving or whether the boat's standing still. Question number 3. Question number 3. The fastest recorded pitch thrown horizontally. That's key. We're always going to do those. That means you have no Vy, 0. It's going to fall 0.890 meters and it's go 8.3 meters away. So what do we know here? You know, x0 is going to be 0. You know, y0 is going to be, well, let's say it's 0.809. I'm sorry. Yeah, 0.809 meters. What's our x final? Problem tells us 18.3 meters. What's our y final? What fell from it fell 8.809, so it ends up in the ground, equals 0 meters. So we know all of those. What else do we know? We know that our a in the y direction is -10 meters per second squared. So that's a typical for our projectile motion problem. And we also know that Vy0 equals 0 meters per second. So let's start solving our problem. If we want to find out how fast Ryan's pitch is, what are we asking? We're asking to find Vx0. Vx0. Well, we know from a projectile motion, Vx0 is the same thing as Vxf. So how are we going to find that? We know from the definition of velocity, it's the change in x over the change in time. A velocity in x direction, change in x over change in time. Do we know how far the change in x was? Yeah. We've got those. Right, so this is going to be 18.3 meters. But what's our change in time? We don't know. So how are we going to find our change in time? What other information do we have? Well, we have information about our y's. We have information about our y's. And if you remember from what our y equations are, we had one that looked like this. Yf equals y0 minus 5 meters per second squared times t squared. So there's an equation for t. We know yf, we know y0. We can find out what our t is. So we're going to rearrange this equation. And let's plug in our numbers. We're going to see what our yf minus y0. What was our difference? -0.809. We're going to divide that by -5. Then we got to take the square root. .809 divided by 5, 0.1618. Well, now that we know our t, we can take that and we can plug it in up here. And then we can find the velocity of our pitch. We're going to use this trick a lot to find time. Person standing on the edge of a seaside cliff kicks a stone over the edge. So the stone's going to have a horizontal velocity. That's our Vx0. 52 meters above, that's our that is our y0. What's it asking us? How long? So it's asking us for t. Well, what are the pieces that we know? We know x0 equals 0 meters. We don't know x final. We know y0 equals 52 meters. We know yf, right? Fell into the water, so yf is 0 meters. We know the x0 is 18 meters per second. And we know Vy0 is equal to 0. We're almost always going to have this. I don't think I'm going to give you one that doesn't have that condition. So we're asking for time again. How are we going to figure out time? We're always going to go to that one equation here that we were just using. Do we have enough information to do this? This equation here. Do we have enough information to do that? Yeah, we do. T equals the square root yf minus y0 over -5 meters per second squared. If we plug in our numbers here, what are we going to get? Yf minus y0, it's going to be -52 meters. What's our 5 meters per second squared? So let's take 52 divided by 5 and then take the square root. And we're going to take the square root of that. We get 3.22 seconds. 3.22 seconds. All right. Now I've got our t. Let's figure out what our next question is. Whoa. With what speed and what angle does the ball strike the water? With speed and what angle? So if we're trying to find speed and angle, what do we need? We need to find our Vx, our Vxf, and we need to find our Vyf. We need to know the components of our velocity vector. Well, we know that our Vxf, that's going to be the same as our Vx initial. It doesn't change. What's Vyf? It's simply -5 meters per second squared times t squared. Times t squared. Let's plug in our value of t squared, t. And what do we have? We're just going to get a -52 meters per second. And this was, 18, I think, for our x. So if we know our Vx and our Vy, we can find the speed. Speed is simply the magnitude of that vector. Square root of 18 squared meters per second plus the square root of -52 meters per second. We get 55. Meters per second. We also need to know the direction. How do we find our direction? Tan to the -1. What's our Vx? Our Vx, our Vy, -52 meters per second. Don't forget that negative sign, very important. What's our Vx? 18 meters per second. We do the inverse tangent of that. Our calculator is going to come back and tell us -70.9 degrees. So there is our speed and there is our direction. Notice it's got the negative sign. That kind of makes sense. If we draw a picture of what's going on here, they kicked it off a cliff. So what's our stone doing? It's going like this. What's our velocity vector? It's below the x-axis. Our velocity vector is pointing below our x-axis. So we do expect this angle to be negative. Our next one. Let's write down what do we know. We have a spine of boat. They're just as they come up even to each other, so they're at the same position. They fall off a 5-meter-high waterfall. SPY speed is 15 meters per second. The official speed is 26. What do we know? X0 for both of them is 0 meters. Y0 for both of them is 5 meters. YF, for both of them, they're going to fall to the water, 0 meters. Vx of our SPY, I'm going to put an S for that, 15 meters per second. Vx, well, we need another thing here. Let's say OF. That's just still, let's say police. Vx of our police is 26 meters per second. Okay. So it's asking us how far apart will the vessels be when they land? Well, we got to figure out where each one lands. How are we going to figure out where each one lands? We got to figure out how long they're in the air, right? So if we look at our X final equation, what is that equal to? X0 plus Vx0 times t. We got to figure out what's this t. The same trick we've done before. Yx, y final. What's y final? It's 0. Y final is 0. Y0 is 5. So what are we going to get? We're going to get the square root of negative 5 meters over negative 5 meters per second squared. What's this equal to? 1 second. So our t is equal to 1 second. Let's plug that in. So xf of our SPY, they both started at 0 position, so it's Vx0. What was the initial speed of our SPY? The initial speed of our SPY was 15 meters per second. And it went for 1 second. So he's going to land at 15 meters. How about the final position of the police? They're also started at x0 with 0. What was their velocity? 26 meters per second. They also flew for 1 second. So they're going to land at 26 meters. So how far apart did they land? How far apart? 26 meters minus 15 meters equals 11 meters. There's our answer, how far apart when they land. So this one had one little extra step. But I want you to see it wasn't hard. It wasn't hard. We got all the way to the end. We figured out how can we figure out where each boat lands. Plugged in the equation for the SPY, plugged in the equation for the police. We got their landing point. Then it's real easy to figure out how far apart they land. Last problem. Baseball rolls off 0.7 meter high desk, strikes the floor 0.25 meters away. How fast? So it's asking us for t. What do we know? x0 equals 0. Y0 equals 0.70 meters. What do we know about XF? Here the problem gives it to us, 0.25 meters. What do we know about YF? 0, because it hit the floor. So let's use our equations. How fast was the ball rolling? So what are we looking for? That's not T. We're looking for Vx. What's the velocity in our x direction? And again, because of there's no gravity, Vxf is the same as Vx0. In our projectile motion, which this is, Vxf is equal to Vx0. It's constant. So we want to find that velocity. Again, how are we going to find it? What was our change in x over our change in time? Well, we can figure out our change in x, right? 0.25 meters minus 0 meters, but we don't know our change in t. Well, we're going to do the same thing we've done in lots of the other problems. What's our change in t? T equals the square root YF minus Y0, or negative 5 meters per second squared. YF minus Y0, that's 0.7, negative 0.7. Plug that into our calculator. What are we going to get? 0.7 divided by 5 equals, and we need to take the square root of that answer, 0.374. seconds. So let's plug that in. Let's get our velocity. That's going to equal 0.67 meters per second. All right, guys, that's it for our review today. Hopefully that helps. If you have any questions, please let me know. And we'll see you tomorrow. Take care. Bye.